please go ahead.
All right, so hi everyone. Our presentation is on the development and application of Storm Tools design load maps. My name is Isabella, and my group members who will wave their hands as I say their names are Blaze, Alexa, Michael, Allison, Joe, Brandon, and Chris. So first we'd like to give some acknowledgements to the people who have helped us during this project. So Dr. Spalding, Dr. Baxter, Dr. Ciatis, and Dr. Swanson were our Capstone advisors. And Chris Damon, Suresh Kui, Jen, and Teresa Green were people who also helped us through URI, so thank you. So here's an overview of which shows a map on the right from the E911 database displaying structural density in the westerly Rhode Island area. During the presentation, we'll begin by talking about our background, problem statement, study objectives, and followed by the methodology, results, and then finish with our concluding remarks. Something to note about our project and presentation is that there is not only ocean engineers in our group, but also civil engineers, making our project unique in a way that we present our information moving forward. So now to give some deeper information about Storm Tools. So it's accessed through an online ArcGIS website and can be used by anyone. And the maps are in high resolution. So in general, Storm Tools is a method to map storm inundation with and without sea level rise for varying return period storms that cover all of Rhode Island's coastal waters. The design elevation maps are expressed in the form of base flood elevation, or BFE, as Brendan previously mentioned. These maps were developed for selected sea level rise cases in order to support specific structural designs. Here are two screen captures from Storm Tools, both for a 100-year storm, to show the design elevation maps. So in the red circles, you can see in the top left-hand corner is for sea level rise 0, and the bottom right-hand corner is for sea level rise 10. The enlarged legend shows the design elevation in feet, and by looking at both maps at a glance, you can see the dramatic change in color difference. So looking closer at the coastline of the bottom map of sea level rise 10, you can see the deep reddish purple color that signifies a greater value than 35 feet. And while in the top right-hand corner, top left-hand corner, you can see the sea level rise of 0 feet map. There's a light green color along the coast. So now moving into our methods for environmental loading. So here's a flow chart to better show our methods for the environmental factors. This is an overview slide based on the FEMA flow chart that was shown earlier. And we generated flood loadings results for hydrostatic, wave, hydrodynamic, and debris loads. The red box are the flood loads that we focused on this semester. Equations on the right show back up our calculations. So here's a more detailed flow chart showing the inputs used for the equations applied in order to generate the flood loading data in maps that we will look at later. The inputs from Storm Tools design stillwater flood depth and design breaking water wave height. The inputs from the user are the width of structure, area, diameter of the pile, and number of piles. There are also constants that we use, which we will explain in the slides to come, along with the listed equations in the middle. This is important to note. Also, how you scale a load to a specific structure is important to note because it involves multiplying the inputs by user box with the equations listed. So this is important to note because the user can then scale their calculation based on their specific structure's units. Here's a slide to show how we calculated the hydrostatic loads. The cartoon on the right shows a visual depiction of how and where the hydrostatic force is applied in comparison to the ground surface and the flood level, which is from the FEMA construction manual. And the equations for the unitized and the total hydrostatic load are shown on the left. We use the bottom equation and application to be scaled for a specific structure. So now we're going to move into the results, first starting with flood loads, and then we'll follow it with the structural. So here we're going to show the different flood loading maps which we were able to get uploaded online with a link thanks to Chris Damon. The link is shown on the slide in blue. So this site is not open to the public, but we were able to upload our maps and have a shareable link. And we wish we could click through the link, but figured it would be easier in the WebEx presentation to show screenshots. So first on this slide, I'm showing the screen that displays the contents of the capabilities of the site and the resulting maps. So on the left side is the area where a scroll menu is available to show the options to select based on what type of map you want to be displayed. Also on the top of the screen, you can see the different sea level rises that have the same drop-down menu for each tab. So just showing a lot of different capabilities that this has. So here's the hydrostatic load at a sea level rise of 0 feet for a 100-year storm. Again, bringing in the image, the little cartoon that we have to remind the audience of our load calculations. In this map, you can see lots of blues and greens, which signifies the low hydrostatic forces of 4,000 pounds per foot along the coast, and even lower inland, around 1,000 pounds per foot. And here, along the pond, you can see a lot of yellows and more green colors present on this map for the sea level rise of 5 feet. And this signifies an increasing hydrostatic load value of around 8,000 pounds per foot for the yellow sections. There's also an orange spot in the middle of the study area, which is a coastal pond that has a load value of less than 10,000 pounds per foot.
So overall, our objective this year was to develop Storm Tools design load maps index based on flooding estimates for a 100-year storm event. This is explicitly including the effects of sea level rise for hydrostatic, hydrodynamic, wave, and debris loading on residential structures in the Rhode Island coastal floodplain. Functionality of the SDL index was evaluated by applying the methodology to the design of a typical residential structure on grade and one elevated on piles in the Watch Hill, Rhode Island area, again for varying sea level scenarios. Rational damage curves were developed for each design load using structural analysis software or compared to existing empirical curves. That's what you just saw in the last few slides, were really the culmination of all the structural analysis.